So now can you hear me? Can you all hear me now? Can you all hear me now? Yes? Okay, fine. So finally we are on track. Okay, so good. So if you see in the first module of this fluid mechanics course, yeah, thank you, Rahul. So see here, in the first module of this fluid mechanics course, we have seen certain properties of fluids, correct? So basically, we have seen few important properties like viscosity, capillarity, surface tension, and all of the specific weight density and all of the properties of fluids, correct? So now we go on to the next part or the second module of this course, which is fluid statics. Okay, so basically, you know what is statics, correct? So statics is a part of mechanics where we deal with bodies at rest or moving with constant velocity, correct? So here we go for fluid statics, and this is the first lecture on this fluid statics. Okay, so in this course, in this module, basically we deal how the pressure varies within the static fluid and how is this pressure measured. Okay, so basically we'll understand what is pressure, and we'll also find certain techniques to measure pressure within some fluid. Okay, so this is what we have focused. Now let us go back. First of all, let us identify what is the difference between stress and pressure. What is the difference between stress and pressure? Let us try to identify this. Okay, so what is stress? What is stress and what is pressure? In your words, first of all, so you please try to respond, and in your words try to point out a bit of difference between stress and pressure. All of you, please try to type something. Okay. Internal resistance versus external load. So generally, yeah, I think you are near to the idea. So basically, if you take a solid, if you take any solid in general, and let us suppose you have applied some, external load on this. Okay, let us suppose you have applied some external load on this. For example, this is P. Then what happens? Since the molecules on solids are very much closer to each other, the molecules which are exactly on this layer tries to get dispatched from this location because of this external agent. But because of the cohesion present in the nearby molecules, there is some internal resistance developed for the movement of these molecules, correct? So basically, whenever you are trying to displace this edge or displace this layer of molecules by applying an external force P, then there comes some internal resisting force. There comes some internal resisting force within the solid, correct? Internal resisting force within the solid. And this internal resisting force, let us suppose if this is R. Now, what is stress? Stress is this internal resistive force, per unit normal area. So you can write normal area. Let us suppose if you are talking about, or in general, if you generally write about shear stress or normal stress, you can write just area here, correct? So this is stress, which we know. Now what is pressure? Stress is an internal effect, correct? So what is pressure? What is pressure? So this stress basically some internal resistive force per unit area, but pressure is, you can see, let us suppose if there is some body here, which is, let us draw some fluid, let us draw some bulk of fluid. So when you have some bulk of fluid, then what does it happen? When this body is in some bulk of fluid, there is some external effect which is applied on this body by this fluid, correct? So basically pressure is, you can write, pressure is the external normal compressive force. Normal, and of course when it's normal it can be compressive as well as tensile, but of course in pressure, whenever you place any body within some expanse of fluid, the pressure or the force from this fluid try to act on this body, and this external normal compressive force per unit normal area, is called stress. Pressure, correct? Is called pressure. So basically this is the difference between, good evening Vamshi, so please see here. So basically if this is the definition of your stress, then that's the definition of your pressure. So in case of pressure, what happens, the surrounding fluid tries to exert some force on this body, of course normal to this, correct? So let us suppose in this case you have, okay, so let us suppose I am trying to identify some, so this is the basic difference between stress versus pressure. So basically pressure is external effect on some body, whereas stress is internally developed resistive force per unit area. So this is pressure, and we in this case of this fluid statics, we study what is this pressure variation, and of course what is this, how is this pressure associated with different elevations inside a static fluid. We will study all these cases. So are you all clear? Are you all able to identify what is the difference between stress and pressure? The stress is something which is developed internally within the body, whereas pressure is something that the external normal compressive force per unit normal area. Clear? Now let us go to one very basic law in fluid statics, which is called the Pascal's law. Okay, so what is this Pascal's law? Let us try to identify what is this Pascal's law. What did Pascal say? Look, in a static fluid, yeah, I am fine, Rahul, thank you. So let us suppose in an expanse of fluid, in an expanse of static fluid, okay, this is static fluid. In an expanse of this static fluid, now if you take any point within this fluid, then what did Pascal tell us? What did Pascal tell us? The pressure exerted by the surrounding molecules on this, means basically the pressure at this point is same in all the directions, correct? This is what Pascal told us. If you take pressure in all the directions, then in every direction this pressure is same. This is what Pascal told us, correct? So now mathematically let us see how this pressure in every direction is equal. Okay, so see here, let us first write the Pascal's law. So in a static fluid, and what do I mean by static fluid? On this fluid there is no tensile stress and also there is no shear stress. Okay, there is only normal compressive stress. So whenever the fluid is static, so in a static fluid, the pressure at a point exerted by the surrounding points is same in all the directions. This is what Pascal told us, correct? So basically if you take any static fluid, inside the static fluid, at any point, if you locate a point within this bulk fluid, then at that point the pressure will be same. Of course it's normal compressive stress, but that point will be experiencing same normal stress, of course in compressive nature, from all the directions. Now let us try to identify this, how this is happening. Okay, so to identify this, let us take a small wedge inside this. So let us suppose we are taking a small wedge here, a fluid wedge. Okay, so there is some fluid element which is a triangular prism basically. So I am taking out that fluid wedge, and I will show you, if that fluid prism tries to shrink to a point, then the pressure from all the directions will be equal. This is what I want to show you. Okay, so let us try to identify that. So let us try to draw one fluidic prism. So see carefully. Okay, fine. Now okay, see carefully. Let us try to identify a fluidic prism, and you can draw along with me by taking some time in your notebooks. Okay, so fine. So let us suppose this is a triangular prism, and this prism is actually this a minute fluid element which I have taken here, and what I have done in this page is an exaggeration of that. Now let us take a right-handed coordinate system basically. So let us take a right-handed coordinate system, x-axis, y-axis and z-axis. Okay, so let us suppose this is your x, this is your y and this is your z. And let us suppose this fluidic prism which is here has some finite dimensions, and this dimension is dx and this of course is dy and this is dz. Let us look at the points O, A, B, C, D, E. Let us suppose these are the points. Okay, now let us suppose if this fluid is in or this element is at particular point, and let us suppose at that particular point the pressure in this y direction is Py. Let us try to identify the things. Let us suppose the pressure on this face is Py. Okay, so let us write that Py. Next, let us suppose this angle is theta, some arbitrary angle. So this angle is theta. This theta is arbitrary, which because I am taking this because at any orientation I want to show you the pressure is same. Okay, so this is theta, and on the bottom plane, let us suppose this is the pressure that's acting on this bottom plane, and of course that's in the direction of z. So let us suppose this is Pz, and let us suppose the normal force acting on this plane of the fluid is something like this, and which is Pn. Pn. Clear? Can you all identify that there is a fluidic prism here, and of course this prism is some small prism that's taken here, and for the analysis purpose to show you at a point I have plotted pressures in all the three directions, which is along this y direction, z direction, and also at some angle which is arbitrary. Is that clear to you? Are you all able to identify the three stresses that are acting on this? Of course, pressures Py, Pz and Pn. Are you all clear? Can you get the idea that there is a triangular prism here and there is some pressures that are acting on the left face, bottom face and this top face? Correct? Yes? So please do respond. Is that clear to all of you? Yes? Now there is also one more direction. I can take along this x direction, but when this Px, that's what I am telling you, Mansing. Now if I take some pressure along this, look carefully. If I take some pressure which is normal to this outer triangle and similarly onto this back triangle, then for the equilibrium the sigma fx has to be 0 and both these pressures will get equal. Okay, and moreover you see this element is very small, so the net pressure exerted by the fluid on this particular face will be very small. So even though if you consider Px, that gets cancelled out, so I am not taking, to make the analysis a bit easier. Now let us try to identify carefully. This fluid prism means this fluid element is in static condition. If this fluid element is in static condition, then you know F bar is equal to mass times acceleration bar, and you know whenever this fluid is in static state means this pressure means this prism is in static state, this acceleration vector is 0, which means net force on this component is 0. Correct? Net force on this component is 0. Now if you consider the forces that are acting on this prism, look what are the forces. Py into now this Py is acting to the face, is acting perpendicular to the face BCDO, correct? So what is the area of this face BCDO to which this Py is normal? Definitely this dx into this dz. So dx into dz. This is what we can write here, correct? Similarly, what about this Pz? This Pz is acting normal to the plane DEAO. So definitely this Pz into what is the force that's acting here? This dx into dy, which is this area dx into dy. Next, if you take this particular prism, then this is the plane that's on which this Pn is acting normal. So this dimension is dx, because you see this, if this is dx, then this AE length is also dx. And what about CE? From this particular triangle, you know this height is dz. So definitely this side will be nothing but dz by sine theta, correct? So Pn into dz by sine theta into and dx is the phase. So these are the forces that are acting on place, correct? Initially we have taken some pressures, and these pressures when they are multiplied by some areas on which these pressures are acting, we'll get the forces. So can you all understand in an outset that these are the three forces that are acting on this fluid prism? Yes or no? Are you all able to understand this? Yes? Yes? How sine theta? Because see, from this triangle you can write sine theta is equal to dz divided by CE, and this implies CE is equal to dz by sine theta. Okay, because this area is nothing but the CE into AE, and AE length is dx. So CE is nothing but dz by sin theta from this triangle. So Pn into dz sin theta into dx. Is that clear now? Is that clear now? Okay. Now, under the action of these forces, this fluid element is static. So if this fluid element is static, then definitely sigma Fy has to be 0 and sigma Fz has also to be 0. Correct? And sigma Fx is anyhow 0 irrespective of this dimensions. Now see here. Let us consider sigma Fy is equal to 0. Let us try to plot all these forces in a concurrent force system. Okay. So let us try to plot all these forces in a concurrent force system. Let us suppose we have created one concurrent force system here. Fine. So on this concurrent force system, let us suppose if this is y direction and if this is z direction, then what are the forces that are acting? This py into dx dz is acting horizontally towards y, correct? So we can write a force which is acting like this, and of course this force value is py into dx dz. Next, what is the other force that's acting vertically upwards? This pz into dx dy. So we can also take this. So see here, if there is some force in this direction, then this force is pz into dx dy. Next, what is the other force that's acting in this direction? So you can see this is nothing but Pn into dz by sin theta into dx. These are the three forces that are acting concurrently. Now see carefully, why I am telling you concurrent? Because this is very small, so all the forces will be passing through the centroid of this prism. Now see carefully, if this is the case, Pn into dz by sin theta into dx. Now tell me one thing, the angle between this inclination and horizontal is theta. Now what will be this angle? What will be this angle? All of you, the angle between this horizontal and the inclined plane is theta. So please tell me what will be this angle? What will be this angle? All of you, please respond. What will be this angle? Theta, correct? Because angle between two lines is same as angle between their normals. So if this angle which is here is theta, then this angle here is also theta, correct? So now, if you resolve this force into two components along this y and z directions, see carefully what happens. Let us suppose I am resolving this force. So if I am resolving this force, then I have, this is Pn dz by sin theta dx into this component will become sin theta. So sin theta gets cancelled and we have Pn into dx dz, correct? Yes or no? If you resolve this force along this y axis, then this angle is theta. So the force acting along this negative y will be Pn dz by sin theta dx into sin theta of this. So sin theta gets cancelled and Pn dx dz is here, correct? Next, if you try to resolve this in this direction, so see carefully, if you try to resolve this in this direction, this force will be Pn dz dx, of course, divided by sin theta into cos theta, correct? Because this is the angle this is the side which is in touch with this line. So basically this angle will be into cot theta, correct? This is what you have. Now this is the complete force system, and this, of course, this force is resolved along the y and z directions. So for this fluid element to be in equilibrium, sigma Fy has to be 0. So if you apply sigma Fy has to be 0, then there are two forces which are acting along the y axis. This one Py dx dz and Pn dx dz. So this implies Pn or Py dx dz minus Pn dx dz is equal to 0. So if you see, this dx dz gets cancelled from both sides and Py is equal to Pn. This is what we have, which means this normal stress on this plane is equal to the stress that's the pressure that's acting on the y direction. Next, similarly, if you write sigma Fz is equal to 0, then look carefully. Along with all these components, we have one more excess component. What is that? Along with all these components, we have one more extra component, extra force that's acting. What is that? Nothing but the weight of the block, correct? Nothing but the weight of the block. So see here, So see here, there is nothing but the weight of the block which is acting. And what will be the weight that is acting? Weight of this block is nothing but, if the density of fluid is rho f, then weight is equal to rho f into look, what will be the volume of this solid? Area of this phase triangle, which is half times this dx, or this dy into dz. So half times dy into dz into the thickness of the block. So the block is of thickness dx out of the board, so into dx. This will be the volume. So density into volume will give you the mass, and of course into gravity will give you the total weight of the block. So if you write sigma fz is equal to 0, and of course here the weight will be acting vertically downwards. So let us plot that even. So here there will also be weight. You can write weight which will be acting here. So if you write sigma fz is equal to 0, then what are the forces which are acting upwards? What are the forces which are acting upwards? So you can clearly see Pz into dx dy. Pz into dx dy minus, what is the force which is acting vertically? This component Pn dz dx cot theta, and from this triangle what will be cot theta? Look, this dimension is dz and this dimension is dy. So what will be cot theta from this triangle? Dy divided by dz, correct? Cot theta from that triangle will be dy divided by dz. Minus, there is also weight which is acting. So rho f g into half times dx dy dz. This value is equal to 0. Okay, this is what we have. But now, if you want to converge this complete triangular prism to a point, then what do we have? This dx should tend to 0, this dy should tend to 0, and this dz should tend to 0, correct? In order that if this prism want to be a point, then definitely dx should tend to 0, means dx has to be very small. Similarly, dy has to be very small, and also dz has to be very small. In that case, this complete dimension shrink and they attain a particular point, correct? Now, if these are very small, can I neglect this term dx into dy into dz? Yes or no? So please respond. Can you neglect this dx into dy into dz product? Because since dx, dy, dz are very small for this prism to become a point. Yes or no? So please respond. Please do type in the chat box. For this prism to shrink to a point, definitely these are the things, and dx product into dy into dz, this should be 0. So let us suppose we are neglecting this term dx dy dz to 0. When you neglect this to 0, then you can cancel this dz and dz here, of course, in this cut. So what is left with you? What is left with you? Pz into dx dy is equal to or minus Pn times dx dy. This has to be 0, and dx dy gets cancelled. So Pz should be equal to Pn, which means you got one more thing, Pz should be equal to Pn, which means that's why I am not telling equal to 0. Okay, they are tending to 0. There is a difference between these two. Rahul, when I taught you mathematics, I told you at limits dx is equal to 0 is something different from dz. I mean dx tends to 0. Okay, dx tends to 0 means this dx dimension is very small in nature. Okay, so that's why we are neglecting the product, but we are not neglecting any of this two multiplications here. Okay, so that's the reason, and which means you have this py is equal to pn and pz is equal to pn. So if you take two directions and if you take the third direction in any arbitrary direction, then definitely we found py is equal to pn is equal to pz. Okay, so whenever this block is very small, so whenever this triangle is shrinking to a point, then the stress from any angle of theta will be same, because you see the end result is out of theta, means actually in the end result you had no involvement of theta here. Py is equal to pn and pz is equal to pn, and this pn is defined on a plane which is at some arbitrary inclination. So whatever the inclination you take, definitely you have this pn is equal to pz is equal to py, which means for any arbitrary direction, definitely your pressure is same at a particular point in a static fluid. Is that clear to all of you? Is that understandable to all of you? So please do respond. Please do respond. Is that clear to all of you? Did you all understand that whatever the direction of this plane, means whatever might be this theta, means whatever the orientation of this plane, then definitely this pn will be always equal to this py and pz. Is that clear? Clear? Good. Okay, so take some fluid, sir. Yeah, just took. Yeah, please try to cooperate because my throat is a bit down today again. So see here, this is what we have found here. So basically in a static fluid, if you take any point, then the pressure at that particular point in any direction is same. Yes. Now, one very important question that they ask you in interviews. Normally in strength of materials course, you have, whenever you have a biaxial state of stress, look, one interview question that they ask you many times. If you have a state of this triaxial stresses, yes, so see carefully. Let us suppose we are drawing some triaxial state of stress. Now, see carefully. Now, okay, so in this case, if this is your sigma x, similarly this is your sigma xx, this is your sigma yy, and this is your sigma yy, and these are your shear stresses that are acting sigma xy, and of course these are also sigma xy and sigma xy. In this case, what is the radius of Morse circle? Means if you convert this system into a stress tensor, sigma xx, sigma xy, sigma xy, and sigma yy. Okay, so in this case of biaxial stress, so please tell me what will be the radius of this Morse circle in this condition. You know what is the Morse circle, correct? Basically the geometrical plotting of the stresses on a plane. Pushkar, we will talk about that on this coming Saturday at 7 p.m. Okay, no issue. So what will be the radius of this? Let us suppose if you are calculating the principal stresses, sigma 1, 2, which is nothing but sigma x plus sigma y. Okay, I think space won't be sufficient here, so let us write here. If you are talking about the principal stresses, sigma x plus sigma y by 2 plus or minus square root of sigma x, let us put one x and y here. So sigma xx minus sigma yy by 2 whole square plus sigma xy whole square, correct? These are the principal stresses. Now, these are the principal stresses. Now see carefully. If you calculate this value sigma 1 comma sigma 2, do you know what are these values? Do you know what are these values? If you calculate sigma 1 and sigma 2, what are these values? You will get these values, correct? But of course, for this given matrix, please tell me what are the values of this sigma 1 comma sigma 2 here. They are nothing but the eigenvalues of this matrix. Okay, so sigma 1 comma sigma 2 are nothing but the eigenvalues of this matrix, and you know very easily what are the eigenvalues of a 2 by 2 matrix, correct? So for any stress tensor, if you calculate the eigenvalues, you will get the principal stresses. Okay, so sigma 1 comma sigma 2 are the eigenvalues of this matrix. Okay, now what is the radius of Morse circle? The radius of Morse circle is nothing but tau max is equal to half magnitude of this sigma 1 minus sigma 2. Correct? Sigma x plus sigma y is equal to sigma 1 plus sigma 2, because you know sum of two eigenvalues of a matrix is nothing but trace of the matrix. So sigma 1 plus sigma 2 will be equal to sigma xx plus sigma yy. This is clear. Now, if you take the case of a static fluid, okay, so if you take the case of a static fluid, in a static fluid, if you take the pressure at a point and if you draw the Morse circle, what will be the radius of this Morse circle? Look, if this is the pressure P that's exerted in all directions, and of course let us put negative sign, okay, because it's compressive in nature, that's the only intention. So let us suppose if you are putting a negative sign at all points, and since we have seen this pressure will be okay, since this body is of some finite dimensions, let us not write it here because we are taking some body of finite dimensions. Let us put it here. Minus P. Correct? Now, if you derive Morse cycle for this condition, means taking this pressure acting on all the in all the directions is same. If you derive Morse cycle, what will be the radius of this Morse cycle in this case? I want you to tell this. Look, in case of a static fluid, your sigma xy is equal to 0. Correct? Yes or no? So please tell me, whenever a fluid is static or all the layers of the fluid are moving at constant velocity, then the sigma xy is equal to 0. Is that clear? Why? Because if there is some shear stress, then there is some relative motion between the elements we have seen in the first chapter. Correct? Tau is equal to mu into du by dy. So whenever fluid layers are moving with respect to, if fluid layers are having a relative velocity with respect to each other, then there exists some shear stress. But in a static fluid, you want all the layers to move either continuously at some constant velocity, or you assume that the complete fluid is at some rest. So in that case, this tau x, sigma xy means basically your shear stress value has to be 0. Next, you have just seen that the stress acting in the x direction and the y direction, both these are minus P. Correct? So sigma xx is equal to sigma yy is equal to minus P. So in this case, what happens to your sigma 1 and sigma 2? What happens to your sigma 1 and sigma 2? This term will be completely 0 because this sigma xy is 0 and sigma xx and sigma yy both are same. So these two get cancelled off. And if these things gets cancelled off, then sigma 1 or sigma 2 both are equal and they are equal to minus P. So this implies sigma 1 is equal to sigma 2 is equal to minus P. Though in that case, what will be the radius of the Morse cycle? What will be the radius of Morse cycle? What will be the radius of this Morse cycle? If sigma 1 is equal to sigma 2, look, radius of the Morse cycle is nothing but tau max, correct? So, radius of this Morse cycle is equal to tau max, which is equal to half times this magnitude of sigma 1 minus sigma 2. So if sigma 1 is equal to sigma 2, what will be the radius of this Morse cycle in this case? 0. Correct? So this is the reason why they ask you in interviews many times. This Morse cycle actually it becomes a point. But how in Morse cycles, in plots generally if this is your sigma and if this is your tau, then this sigma 1 is equal to sigma 2 is equal to minus pi. So this point becomes, or this cycle becomes a point on negative stress axis, okay, because the pressure is compressive and of course compressive in nature, so it has some negative representation on sigma plane, sigma and tau plane. Is that clear? So this is the Morse cycle for static fluid. Morse cycle for static fluid. Is that clear to all of you? Fine. In many interviews they ask you like what is the radius of the Morse cycle at a point in a static fluid for the state of stress at a point in a static fluid. The answer is 0, okay, which you are seeing here now. And this formula is very quite common, and these values sigma 1 comma sigma 2 are nothing but eigenvalues of this matrix. Okay, is that clear? Fine. Okay, so please respond. Are you all clear till this point? Are you all clear till this point? Okay, so now I hope you people are busy writing your notes. It's okay, you can respond a bit in the chat box. So are you all clear till this point? Yes, fine. So see here. Now let us see what is the physical significance of this pressure. Anyhow, we have seen there is some pressure at any particular point, and of course this pressure is something like this. Then let us try to see why this pressure occurs actually. Pressure is due to mass, because see here. Let us suppose if you take any container. Let us suppose you have taken some container, and let us suppose you have fitted one pressure gauge. Pressure gauges are the gauges which actually they show some reading of the pressure. Okay, so let us suppose inside there is some gas. Let us suppose there is some gas. I thought of giving you the direct equations, but again, a bit of physics will help you at some points in your interviews. So there is some gas like this. So basically, why this pressure gauge shows some deflection? What is pressure basically? Or why there is pressure inside this container? Because of the collisions of these gas molecules with the walls of the container, correct? So at absolute 0 Kelvin, or at 0 Kelvin, means at dead state, will there be any pressure? At 0 Kelvin for this gas, let us suppose if this is some gas, at 0 Kelvin, will there be any pressure? At 0 Kelvin, you know, there is no molecular motion, correct? So all the molecules, they get settled at the bottom of the container, correct? So at 0 Kelvin, there is no molecular momentum transfer between the molecules and the walls. Now, what it does happen at 0 K, pressure absolute, or you write absolute pressure better. So at 0 K, absolute pressure is equal to 0, correct? So let us suppose, look, it's okay Rahul, but any of you, if you are, I need not tell you again in every class, so please, if you're liking the videos, if you like the content in general, you can always like the videos, okay? Or else if you feel that initially I may teach few lectures very good, but later I'll in the class, you can hit the like button only at the end of the course if you like to, okay? That's up to you. So see here, anyhow, if there is some gas molecules, then let us suppose, I'm sorry. So see here, let us suppose I have reduced the mass of this gas to half. Will the pressure remain same? At given condition, let us suppose I have reduced the mass of this gas to half, means I have taken half of the gas. Then will the pressure be same? Will this gauge deflection be same? Will this gauge deflection be same if I remove half of the mass from this container? No, we know this, correct? Because number of molecular collisions that happen in a given time reduces, correct? So this pressure is basically because of mass, correct? So basically, if you remove some of the gases, some part of the gas from this container, then the average number of collisions that occur with this wall decreases. So as a result, pressure decreases. Similarly, let us suppose if there is some bulk of fluid which is here, if there is some bulk of fluid which is here, in this bulk of fluid, let us suppose if I take 2 points, P1 and P2. Can you tell me which pressure, at which location pressure will be high? If this location pressure is P1 and if this location pressure is P2, and both the atmosphere above both the points is same, okay? So can you tell me which pressure will be more? So what is pressure? External effect because of some fluid, correct? So in that case, if you take this layer, the pressure acted upon this layer by this extending fluid is definitely less than the pressure acted by this surrounding fluid at this point, correct? So definitely P2 is more than P1. Why? There is more mass above this point P2 or about this reference plane as compared to this reference plane. So definitely this P2 is more than P1, correct? P2 is more. This is the reason why we need to study this pressure, because pressure is not constant with respect to altitude, and of course there is some variation in pressure with respect to altitudes, okay? So let us learn some interesting facts about this pressure where you may also find some interview questions. Clear? So see here. See how you will identify this. Look. This pressure has very beautiful significances. You know astronauts? Who are astronauts? Who are astronauts? People who travel to space and come back, correct? So see carefully. These astronauts, they'll be putting on a space suit. Space suit, correct? What does this space suit do in general? What does this space explorer, of course. So what does this space suit do in general? Have you seen the photos of astronauts? Anytime they'll be wearing a nice space suit and also some glass closed equipment, so that the gas which is inside the suit or this cylinders doesn't escape out, correct? So why? Because I'll tell you. Normally at standard temperature and at standard conditions, means at mean sea level and 20 degrees Celsius, you have the pressure of 1 atmospheric pressure. Okay, this 1 atmospheric pressure, later when I teach you Torricelli's vacuum and all, I'll teach you this 1 atm of pressure is equal to 760 mm of Hg column, mercury column, basically. Okay, so and normally if you take human body, there will be definitely some blood flowing inside the body. Look, sweat and blood, they don't flow at the same level. Look, for example, many times you will be experiencing small cuts on the surface of your skin, but your blood don't come out, correct? But daily your sweat comes out because sweat glands are very much above the blood vessels, correct? So definitely whenever you take your body, means if you take your skin which is having some hair here, then definitely some sweat glands are located at this location, but blood vessels are located a bit bottom here, correct? You know this. So basically because of the pores present, little pores present, the pressure at this layer will be almost equal to the atmospheric pressure, and that's the reason why when you run and all, your sweat directly comes out of the body. But the pressure at which this blood flows will be around 120 to 80 mm of Hg. Okay, so here it's almost 760, so no issue. Your sweat can come out easily, and see the beautiful creation of God here. Now he has put the blood at a mm of Hg, which is equal to 120 by 80 mm of Hg, and this pressure which is high is called the systolic pressure, and this is diastolic, correct? We know this, systolic and diastolic pressures. So this 120 by 80 mm means the maximum at 120 and minimum at 80 is the mm of Hg pressure at which this blood starts flowing. Now on Earth, what happens? Let us suppose this is Earth, and let us suppose you are standing here. Let us suppose you are standing here. Then what is the pressure here? It's 760 mm of Hg. Look, at 760 mm of Hg, look, the blood inside your body is flowing at 120 mm of Hg, and the pressure which is outside this atmosphere, means on the top of my hand, is 760 mm of Hg. Now if the small pores are present, then because of the force balance, look, let us suppose 120 mm of Hg is equal to some pressure. So definitely let us suppose this is the plane, and if I am pushing this plane with some pressure which is more, and here if I am pushing this with a less pressure, means the area is in contact is same for both the pressures. So if this is 760 mm of Hg and if this is 120 mm of Hg, then will blood stay inside or it should come out? On the surface you have a 760 mm of Hg pressure, but inside your blood vessels, your pressure or the place where blood is flowing, you have only 120 mm of Hg. Then will your blood be safe inside your body? Yes or no? Correct? It should be inside. Now whenever you go to space, is there any atmosphere? If you go to space, is there any atmosphere? Hardly, no, which means your atmospheric pressure in space is almost 0 mm of Hg. Your atmospheric pressure in space is almost 0 mm of Hg, but inside your blood maintains 120 mm. Now what happens if you go to space without space suit? If you go out of this Earth's atmosphere without space suit, without a proper space suit, then tell me what happens? Your blood starts coming out, bursting out of your body, and that's the most painful death it can happen if your space suit fails. Okay, so that's the reason why many space agencies across the globe, they try to design the best space suit for their astronauts who are living the Earth's atmosphere. Is that clear? So this is the reason why these astronauts put on a space suit. Yes. Did you all understand why there is a necessity of the space suit for astronauts? Because the space suit creates an ambience such that they experience the same 760 mm of Hg pressure acting on them, okay, when they put on the proper spacesuit, okay. So that's why if you see the astronaut, they'll be having some small tankers to breathe and also some small tankers which maintains the pressure throughout the spacesuit, okay. So that's the reason why these people put on a spacesuit, because of this pressure difference. Are you all clear? If atmosphere pressure is more, we feel like getting restricted from all the sides, correct? Let us suppose if you are going into the water, then what happens? The pressure inside the water will be definitely more than pressure due to atmosphere because of the weight of the water above you. Then what you will be experiencing? You feel like water is trying to push you, or means you feel that some force is acting on you, correct? So that's what it happens generally. Is this concept clear? Why these spacesuits are important for astronauts? Is that clear to all of you? Yes? Now, fine. So if that is clear, I would like to define one thing for you. See, one proper chart. What is this chart? Look, see carefully. This atmospheric pressure are two types in general: local and standard atmospheric pressure. So what are the standard and local atmospheric pressures? Look, local is, local means confined to some region, and globe is not a flat thing, correct? It's a spherical and it has lots of depressions and elevations, correct? So generally when you have lot of depressions and elevations, then depending on this, whenever there is some common layer of air till here, some common layer of air till here, there is some common air, and of course let us see, the pressure at this point will not be same as the pressure at this point, correct? Because there is some variation in this height. Yes, can you all sense that the pressure at this location won't be equal to this because of the XX weight of the fluid column that is acting here? Yes. So in general, this P-ATM local won't be a constant value. So it's generally normally measured at that particular locality using some barometers, and they'll give you the reading. So to standardize this, they have introduced this P-ATM standard, and this atmospheric standard atmospheric pressure is taken as 101 kilopascals, which is this 760 mm of Hg and all, and we'll see why this is 760 mm of Hg, and when we go to hydrostatic law, basically torsional is vacuum and all. Okay, so this P atmospheric standardized is nothing but 101 kilopascals, because in generally in local conditions the pressure won't be same at this and these two locations respectively. If this is location 1 and if this is location 2, pressure won't be same at these two locations because there is some excess weight of this fluid column acting on this point, correct? So this is very clear. So if I write this, definitely P2 is less than P1 in this case. Now see carefully, let us suppose if this is your pressure absolute. Now see carefully, this is the point where your P absolute is, let us try to write P absolute is equal to 0 at this point. Let us take a reference where there is no molecular motion, and this generally happens at 0 Kelvin, correct? At 0 Kelvin there won't be any molecular motion, and of course let us suppose this is P absolute is equal to 0, means this line is the reference for taking P absolute is equal to 0. Now is the atmosphere is in dead state, means the atmospheric pressure value, is it 0? Absolute value is 0. Is the absolute value of this atmospheric pressure is 0? No, just now we have seen it's measured to be 101 kilopascals around. So if this is the case, let us suppose your atmospheric pressure is somewhere here. Let us suppose your atmospheric pressure is somewhere here. Okay, I hope you can understand the diagram. So see here, this is your P atmospheric pressure. Okay, and of course standardized value. Now why we need to learn this difference, means why we need to study about the pressures which are more than atmospheric pressures and less than atmospheric pressures? See carefully, because I told you previously also, whenever you connect any gauge, these gauges, they don't give the absolute values. Depending upon the atmosphere in which they are located, they give the gauge pressures or vacuum pressures generally. Okay, so these gauges, they never give absolute pressures. Clear? So that's the reason we should know, if a gauge is showing some value, then what is the actual pressure of the gas inside a container, or actual pressure of a fluid at a particular point. We need to identify this, correct? So gauge readings are never absolute values. Clear? So that's the reason why we need to go into this. So let us suppose a gauge has shown you, let us suppose a gauge has shown you some pressure. So this which you are writing here is P gauge pressure. Now, if you take this, if this is P absolute is equal to 0, then you know this complete pressure which is acting till this location, this is P absolute in this case, correct? But when you are measuring with respect to this atmospheric pressure, look, whenever you are measuring this complete pressure with respect to the 0 absolute pressure, this is your actual value. But when in general, whenever your gauge is placed in atmosphere, your gauge reads only this reading, correct? So if you take this reading as the gauge pressure reading, so P gauge, let us suppose that reading you are taking it as P gauge. So see carefully, this is P gauge pressure. So now this gauge pressure is the reading which is given by your pressure gauge, but the actual value of the gas inside the container is this total value P ABS. And why this gauge is giving only this value? Because this gauge is fitted in atmosphere which is already having some P atmospheric pressure absolute. Is that clear? So if your gauge is giving you P gauge, what is your P absolute in case of gauge pressures? P ATM, of course, standardized plus P gauge pressures, or in general, if for more accuracy, you can take the local conditions here. Okay, P ATM local. Let us suppose if you are plotting only P ATM local, so in that case, your P absolute is equal to P ATM minus P gauge pressure, or you can write P gauge is equal to P absolute minus P atmospheric pressure, or P atmospheric pressure is equal to P absolute minus P gauge, because mathematically you can see what's happening here. If this is P ABS and if this is P gauge, look, let us also write one more important thing. This is your P ATM local in general, correct? So these are the pressures, these are the gauge pressures, and these gauge pressures are measured with respect to standard atmospheric pressure reference. Okay, now let us get back to this pressures which are below this, pressures which are below this atmospheric pressure. Okay, so see, let us suppose there is some pressure which is a bit low as compared to the atmospheric pressure. So this is okay. So see here, fine. So this is your P vacuum pressure. So generally the pressures which are less than atmospheric pressure are called vacuum pressures, and the pressures which are more than atmospheric pressures are called gauge pressure. So now your vacuum gauge reads only this reading, correct? So see carefully. If this is your P absolute in this case, if this is your P absolute in this case, and you know this difference, if this is again P atmospheric local, so if this is P atmospheric at the local conditions, then this difference which is here, look, this difference which is here is the P vacuum pressure, means this is the reading of your gauge. So now if you see, if you want to measure if your vacuum gauge shows this particular reading, which is the difference between this atmospheric pressure and the absolute value, so how you will be writing this? P vacuum plus P absolute is equal to P atmospheric local. If you write the absolute pressure, P ABS is equal to, or if you want the expression for this P vacuum pressure, you can write P ATM local minus P absolute, or in general, if you want the expression for absolute pressure, you can also write P ATM minus your vacuum gauge reading. Okay, so this is how basically you will be finding absolute pressures in case of gauge pressures and also vacuum pressures. Is that clear to all of you? These relations are a bit important, because normally in your experiments, if you go for some research work and if you conduct some experiments, your gauges never give the absolute readings, they give the gauge readings, and it's your responsibility to convert those gauge readings into the absolute pressures. Okay, because the gauge gives the reading depending upon the atmosphere in which this gauge is located. Clear? So this is the reason. And did you all understand this chart? Why this chart is important? Yes, P vacuum is less than P ATM. Oh, I'm sorry, I think I made a mess here. P vacuum is equal to P vacuum plus P absolute is equal to P ATM local, correct? So P vacuum is equal to P ATM minus P absolute, correct? So this vacuum pressure is less than this atmospheric pressure. Okay, that's what your vacuum cleaner works out, correct? In vacuum chamber, what does it happen? Outside your pressure is atmospheric pressure. Look, let us suppose if this is the vacuum cleaner tube and I'm putting here, then what happens? Inside this pressure, there develops a pressure. Inside this tube, there develops a pressure which is much less than the atmospheric pressure. So what happens? Whenever there is some dust here, and if this is at high pressure, this is at atmospheric pressure, and if my tube in the vacuum cleaner is having a pressure which is less than this atmospheric pressure, then definitely things flow from high pressure to low pressure. So definitely the dust particles which are here are sucked into the tube because of the pressure difference. Is that clear? Yeah, gauge pressures can be positive, negative or zero. Look, gauge pressures in sense like your pressure gauges, your vacuum gauges will give you the pressures which are a bit less, okay, means than the atmospheric pressure. Look, no ways absolute pressure will be negative, okay, absolute pressure will be either 0 or it will be more than 0, but you can't tell absolute pressure is negative. But comparing to this atmospheric pressures, you can tell these vacuum pressures are called negative pressures and these gauge pressures are called positive pressures, okay. But if you talk about absolute values, no way you should have your absolute pressure to be 0, because your pressure can't go beyond this, because either there will be some molecular motion or there won't be any molecular motion, okay. So in the least case, the absolute value has to be 0, but it can't be negative. Fine. Is that clear to all of you? Are you all clear till this point? Yes or no? So are you all clear till this point? Will the absolute pressure be negative at any case? Will the absolute pressure be negative at any case? In general, no. Correct? So absolute pressure won't be negative in general at any case. Fine. So this is how you will be converting your, or you will get the absolute values from your gauges. Okay. So once the gauge reads some value, this is how you will be having this. Okay. So are you all clear with Pascal's law also? Are you all clear with the Pascal's law? And of course, this is some mathematical consideration. So are you all clear with Pascal's law? What's happening here in this case? Fine. So see now. Let us try to understand some physical phenomena that happens in general life. Yes, if both are given, you can take local. That's why I have taken local in these cases. Okay, because these gauges show the pressure depending upon that particular locality, this gauge which is here. So now let us try to identify one, some beautiful consequences of pressures. Correct? So let us suppose there is some mountain here. Let us suppose there is some mountain. Okay. So now let us suppose this is point 1 and let us suppose this is point 2, and definitely a mountaineer is trying to climb this mountain. Okay. So can you tell me where this pressure will be more, here or here? At 1 or 2? And troposphere is still here. Let us suppose troposphere is still here. So please tell me if this is point 2 and if this is point 1, at which place pressure will be more, P1 or P2? Definitely P1. Correct? So P1 is greater than P2 because of the excess weight of the fluid column, which will be here. This is one thing that is clear. Now at higher altitudes, what happens? At higher altitudes, what happens? Look, normally if you take your body, your blood pressure is say, and your skin is also fat, good enough to block all your blood that's coming out. But there will be few points in your body where your vessels are very weak. Example, your nasal vessels. Correct? If you see your blood vessels in nose, blood vessels in nose. So what happens? These vessels are very weak in general. That's why generally if I punch my hand here, definitely I get some pain, but not too much extent. But if I punch my nose on here, I'll definitely experience some more pain, because these vessels which are here are very weak and they get ruptured very easily. So in high altitudes, what happens? Whenever, if you take things like Mount Everest and all, where there are 8 kilometers, 7 kilometers height and all. So in that case, as this person is climbing up, here the pressure starts falling, correct? And he reaches a particular point where his blood starts, pushing his blood vessels in nose. Means the blood which is inside this nostril vessels, it tries to burst out, and that's the reason why few people, when they go to high altitudes, they experience breathing problems, and they are also they also experience this nose bleeding at higher altitudes, okay, because of this pressure differences. Clear? So that's the reason why they carry an oxygen tank with them when they are trying to trek any mountain. Is that clear to all of you? Because at this particular point your pressure is very low, and whenever your height is so much high as compared to this at mean sea level, then this pressure will fall. And of course, since your nasal blood vessels are a bit weak, and since the blood pressure inside is 120 mm, still that blood tries to pinches out of this nasal vessels, and that's the reason why these people, they experience a nose bleeding problems and all. Now, one more important consequence, look, of this pressure. What is this? Pressure cooker. What is the effect of this pressure cooker? What is the effect of pressure in this pressure cooker? No, see carefully. If you take substances, phase change of substances on a TS plot, for example, I am going a bit into thermodynamics, to which many of you are familiar. So let us suppose if this is the TS plot, so tell me if this is one pressure, if this is P1 and if this is P2, can you tell me which pressure is higher normally on a TS plot? If you go to a bit of thermodynamics, can you tell me if this is P1 and if this is P2, what happens? This is for water. I am drawing for water, okay, for water, okay. So P2 is more than P1, you know this, which means if I take this as my saturation temperature in both the cases, T2 and T1, then your T2 is more than T1, correct? So as your pressure increases, your boiling point of the water increases, correct? If you take rice cooks at around 130-135 degrees Celsius, correct? But normally water boils at 100 degrees Celsius. So in olden days, if you see, they would have taken one vessel, they would have taken some vessel basically. In this vessel, they used to cover this with a lid initially, and inside this, they used to boil water initially, correct? They used to boil this water. Now, what is the physical thing behind their intuition? Whenever in olden days, when they used to cook rice manually, means without the help of rice cooker and all, they used to cover this container with a lid and they used to raise the temperature of the water. What is the meaning of this? Whenever your volume is fixed, then definitely these gases which are getting developed because of the boiling of water, it cannot push the lid, correct? And in few cases, whenever this steam is strong enough, you see your lid dancing on the top of the plate, correct? Have you seen that in your childhood at any time? Normally, if you place a lid on the top of any vessel and if you pour water and if you keep on heating this, then what happens after some time? The steam generated inside this will be so strong such that this lid will start moving. Means at least it starts shaking on the top of the vessel. Okay? The reason behind this is the water which is here is almost superheated. Means the steam which is here is almost superheated and there is some continuous phase change that's happening, and this water temperature is beyond 100 degrees Celsius. Okay? This is what it happens. Now in this hot water they used to put some rice and the rice used to get cooked. But in case of pressure cooker, what happens? Normally if you see, this lid used to have some small pores so that when steam come out of this holes, they used to recognize that okay, the water is ready to boil the rice. So they have take out this lid and they used to put the rice and they used to close the lid. Okay? This is what they used to do. Now in case of pressure cooker, what does it do? Look, in case of your pressure cooker, you are having small lid, this vessel kind of thing on the top. Okay? What does this vessel kind of thing used to do? Normally this is a closed system because this weight of the petcock is good enough so that it can block some weight of the the pressure that is opposing by the steam from the downwards the cooker. Now if you start heating this cooker by pouring some water and putting rice together, now when you are heating this cooker, this is a closed system. In this case there is open system, so here almost the pressure will be similar to atmospheric pressure because of this holes present on the top of the lid. But now in this case, this is completely a closed system, so if you keep on heating, the pressure rise here in this case, if this is happening, and also there is some pressure rise in this cooker, in which case your pressure will rise fastly in that normal manual cooking or in this pressure cooker. In which case, in case of either manual cooking or pressure cooker, your pressure starts increasing faster. In which case, in that or this, in cooker case or in lid case. If I call this as 1 and if this as 2, then in which case your pressure starts raising faster. Cooker means one thing, pressure cooker, of course. So here if P1 is less than P2, and definitely if it takes less time to reach P2, which means let us suppose this is 130 degrees Celsius, where this is good enough to boil the rice. So if you want to reach pressure P2 in both the cases, because your rice is same in both the cases and water is also same and the atmospheric conditions and all are same. So if you are reaching 130 degrees Celsius slowly here and definitely faster in this case, then your rice gets cooked faster in this case. Okay, because this is a closed system and this petcock is, the indication is such that whenever there is steam inside this, and still if you are supplying heat, as this steam is pushing this lid, trying to push this lid here, definitely through the small valve which is present here, the steam tries to go into the valve and it tries to push up this petcock. That's what you experience as a whistle in a pressure cooker. Okay, normally whenever a pressure cooker whistle is raised up, you see a steam, lot of steam getting escaped, correct? Because whenever this steam is of enough pressure, this gets out through the valve and it tries to push the whistle which is on the top of this pressure cooker. Is that clear to all of you? And in this case of pressure cooker, since by creating a closed system, whatever the heat you supply, it's all utilized to increase the pressure and you will reach this higher pressure in a very less time in this pressure cooker. Okay, so all these are very beautiful consequences of this pressure. Are you all clear till this point? Are you all clear till this point? Yes, boiling point increases. So whenever this boiling point is increasing, then definitely you will take less time to reach this pressure and you will take very less time to reach this pressure, and here in this case you reach a higher temperature as compared to that you will get in this open lid case. Clear? Are you all clear till this point? Are you all clear till this point? So please do type in the chat box. Are you all clear till this point? Yes? Did you all understand what does a pressure cooker do in your life daily? Yes or no? Clear? I'm sorry, clear? My throat is giving me so trouble today. How quick? You need to go into a bit of thermodynamic analysis. Okay? Clear? So all these are consequences of pressure. So you have also seen how to measure this absolute pressures in case of gauge pressures and vacuum pressures as well, and all these are some applications of pressure. Okay, so we got the concept of pressure and we also seen this Pascal's law, and Pascal's law tells that in a static fluid, means in a bulk of static fluid, at any point the pressure will be same in all the directions at that particular point. Is that clear to all of you? And how this 1 atmospheric pressure is equal to 760 mm of Hg, we'll see when we go to hydrostatic law, and there we'll go for barometers and Torricelli's vacuum and all. In that case, we'll look at all these things. Are you all clear till this point? I'm looking at the comments, so please do type in the chat box. Are you all clear with these points that we have discussed so far? Did you all understand why there is a need of spacesuit when you go out of Earth's atmosphere? And why when the mountaineers are trying to trek a mountain, there exists some nasal bleeding for them? And also, what does this pressure cooker do in your day-to-day life? Okay, and few interview questions that are asked from today, they'll ask you what is Pascal's law, and of course they'll ask you, if you look at if you try to draw a Morse circle in case of a static fluid, what will be the radius of the Morse circle? The answer is 0. Okay, and the Morse circle reduces to a point in case of a static fluid. Is that clear? And also, I think one extra point that you learned in today's class is that principal stresses sigma 1 comma sigma 2 are nothing but eigenvalues of the stress tensor. Clear? Are you all clear till this point? Yes? Okay then. So, okay. So fine, again I am telling you, if you are liking the content, you can like the videos, or if you have the doubt that initially I will be teaching good and later I may not teach that good, then you can wait till the completion of this course and you can like at last. But of course, if you are on this channel for the first time, please do subscribe immediately, because I am telling you, if you are launching some course, you will be get notified every time we put some new video or something, so that you can watch it from the beginning. Okay, and every Saturday, as I told you, at 7 o'clock, we will be having some non-technical session regarding admissions or some other outlook on different domains, and also at 9:30 p.m. we'll be having the problem solving session on all the topics which are covered in that week. Okay, so coming to the next lecture, we'll talk about this hydrostatic law. I hope all of you have understood this concept of pressure and Pascal's law. So in tomorrow's lecture, we'll go for this hydrostatic law, and that's our lecture number 2, and we'll see what is the pressure acted upon a tip of a submarine as well. Okay, so no issue. We'll look at all these points in very much detail as we are doing it in every hour lecture. Okay, so next, as I told you, every Saturday we are doing one non-technical session. So this Saturday on 13th of March at 7 p.m. we would like to reveal you all the facilities that are within IIT Madras, or all the opportunities that are in IIT Madras. I myself is a IIT Madras, I have spent my good time in IIT Madras during my masters, and also he is VH from IIT Bombay, who has enough knowledge on all this admissions, cutoffs and all. So we both guys will definitely take on this session. So unexplored IIT Madras, I personally had some 2.5 to 3 years, nearly 3 years experience in the campus. So definitely I'll reveal you what are the opportunities present in and out over there. Okay, so you can always hit the like button of this kind of videos. So definitely they'll, as likes are more, definitely the content gets reached to others as well. Okay, who are looking for that. Yes, PSUs do equal to GATE, no issue. Okay, so coming to our batches, we have started offline as well. So online, anyhow, we are providing you for free as of now. So offline is also going on. So for offline, we have started regular batches. Like the first batch is going on 1st of March, second is on 15th of March, and third is on 29th of March. But if you are planning to join, then you can definitely join us immediately, because the soon you join, the more the chance you will get to revision for some few subjects which we are going to take over. And generally the timings of this batch are being from 2 p.m. to 7 p.m. daily, and of course this batch will prolong for 5 to 6 months. And Negi sir is already a first ranker, and also he will be guiding us in all these things. Next, this is our classroom picture that I always show you, and you can definitely find some sheet here. This is a pic, of course, an old pic in the sense that was clicked in the last week, so you can just see the things. There is also one regular, long-term weekend batch which is going on. So you will be having class on every Sunday in the offline base, so which is supported by some tests through the Infinity app. So you can always join this offline long-term weekend batch as well. So for GATE 2022 and GATE 2023 as well. Clear? So these are our contacts of Engineers Hub. This is the YouTube channel of Engineers Hub, where you can always find some lot of free content. And also I am telling you, in the YouTube channel of Engineers Hub, we are maintaining one exclusive playlist for job notifications. Okay, so what are the recent job notifications that are out? Immediately we are trying to put some information on those job notifications, and these are the official Twitter, Facebook and LinkedIn profiles of Engineers Hub, and you can go to any one of this for getting the daily updates, and very soon, as soon as we launch them. And of course this is the two places, these are the two places, Engineers Hub Telegram channels, one for exclusively mechanical and one for all others excluding mechanical. So you can subscribe to all these Telegram channels, so that you will be getting your notes of this class daily, because we are posting the notes of this class daily on day-to-day basis in these two groups. Okay, so you can definitely subscribe to these two Telegram channels, and this is your Engineers Hub official website, and you can get all the useful information, all the important updates of Engineers Hub in this website for definite. Okay, so is that clear to all of you? Is that clear to all of you? Is that clear to all of you? So I hope things are going fine, correct? Is there any issues to anyone who is on live? I hope things are going fine, correct? Yes? Thank you, Vajnesh. Fine. Then we'll meet tomorrow sharp at 9:30 p.m. and tomorrow's class is one very important class, because tomorrow's class means the hydrostatic law is the principle for all manometry and other barometers and all. So please don't miss tomorrow's class, because hydrostatic law is one very important thing which we deal in fluid mechanics. Okay, so thank you all, have a nice time, good night. We'll meet tomorrow sharp at 9:30 p.m. Thank you all.